Welcome to Maths for All. I'm Aisling Flynn. This is Higher Level. And this video is about statistics, in particular correlation. So let's review scatter plots and bivariate data. So on the right here you see a picture of a scatter plot. So lots of dots scattered around. And it's used for bivariate data. And for numerical data, meaning that you have two variables. On the example given here, we have time per visit, seconds, and unique visitors. Okay, so that might be, I don't know, a tourist attraction or something like that, or a shop indeed. Okay, and what we are doing is we are investigating relationships or trends between the two variables. So that's what we're looking for there. And an advantage of a scatter plot in statistics is that you use all the original data. Now, correlation. Correlation is used in studying those relationships between the two variables. So correlation is a measure of the strength of a relationship between two variables, say x and y. We say x and y are correlated if a scatter graph or scatter plot shows a linear pattern to the plotted points x, y. So when you plot them against each other, do you see a straight line or something like a straight line? If no pattern exists, the variables are not correlated. The three diagrams below illustrate positive correlation, negative correlation, and no correlation. Okay, so let's look at the first one, which is for positive correlation. The variables x and y have a positive correlation. If y increases, then x also increases. And we can see, or we can imagine, a straight line. Whoops, that's not straight. A straight line through all that data, okay? There is some sort of linear pattern, okay? And the points are quite close to what I estimate would be the linear pattern. All right, so if you take a greater value of y, you have a greater value of x. Okay, if you take a small value of y, we have a small value of x. Okay, so there's some correlation there. And that's positive. They're both increasing. Okay, let's look at the next graph. The variables x and y have a negative correlation. If y decreases as x increases. So here we do see a pattern for sure. And I could approximate it by drawing a straight line, or supposed to be a straight line, through the data there. Okay, and you can see if you have a low value of y, it gives you a high value of x. If you have a high value of y, you have a low value of x. Okay, so as one increases, the other decreases. So this is shown as a negative correlation. Okay, and on the third example here, the variables x and y show no linear pattern. So you could draw a circle around them. Okay, there's no pattern. You can draw no conclusions from that. There is no correlation. Okay, if you can draw a circle around the data, then there's definitely no correlation. If you can draw an oval shape around the data, well then perhaps you do have correlation. Okay, depending on how narrow that oval shape is. Okay, let's look at some more. And this example here, a scatter graph or scatter diagram is a graph consisting of points plotted on an xy plane. Okay, so you have a horizontal and a vertical axis. Each point represents the values of two different variables. So we're on two different variables. Okay, such as heights and weights. So that's two measurements of different individuals, of people. Okay, two measurements from people. Such data connecting two variables is called bivariate data. So bi refers to two, okay, two variable data. The table below shows the number of ice creams sold by a shop over a 12-day period. So number of ice creams, that's one variable, but also they've recorded the average temperature in degrees Celsius, okay, on the day that they recorded the sales of ice creams. So we have one variable and we have two variables. So this is bivariate data, and we're asking, do you think there is a relationship or connection between the daily temperature and the amount of ice cream sold in a shop? So quite possibly yes, okay. Using the horizontal axis for temperature and the vertical axis for numbers of ice cream sold, we get the following scatter graph. So when you go to draw your scatter graph or scatter plot, it's important to label your axes correctly. So the temperature is here on the bottom, and that's measured in degrees Celsius. Okay, and on the side then we have the numbers of ice creams. Okay, and you see that the scales are set out nicely to include all the information from the table. Okay, so let's look at how some of those are plotted. So when the temperature is 10 degrees, or when it was 10 degrees, one ice cream was sold, and that's this piece of data here. Okay, when the temperature was 12 degrees, we had 5 ice creams sold, and so on. Let's take the very last piece of information. When the temperature was 16, there were 30 ice creams sold. So 16 and 30, that's this piece of data here. Okay, and what do you see? Well, I definitely see a trend. Okay, I can imagine a straight line going through that data. Okay, or I can draw a very narrow oval around them. Okay, so there is definite correlation, and that makes sense. On hotter days, more ice creams are sold. So the scatter graph shows that the number of ice creams sold increases as the temperature increases. So this is a conclusion or a summary of the graph. The scatter graph shows that the number of ice creams sold increases as the temperature increases. Since the points lie close to a straight line, we say there is a linear relationship between the two sets of data, and in fact I would say that this is quite a strong, okay, there's quite a strong, you don't have to use your imagination very much, a strong positive correlation between those two variables. Okay, strong positive correlation between average daytime temperature and number of ice creams sold. Okay, so the correlation is high or strong, right? We can use that word as well, is strong. Okay, if the points are close to a straight line. Okay, and the correlation is low or weak if the points are more spread out. Okay, it is possible to have strong and weak positive correlations as well as strong and weak negative correlations. The scatter diagrams below illustrate these possibilities. So if you can draw a shape to enclose all your data, that's quite a narrow oval, we'll call that strong, and the line is rising, x rises or increases with y, both increases, so it's strong positive. Now if you look at the next one and try and enclose them, you see it's much more spread out. It's a much broader shape that I draw around it, and so we say this is a weak positive correlation. Okay, and the same can be said for the negative correlations. So as x decreases, y increases, and vice versa. Okay, that one is strong negative, and the last example here is much broader, much more spread out, and that is weak negative. Okay, so an example here. The table shows the weights and heights of 12 people. and we're asked to draw a scatter graph to show this data. Describe the strength and type of correlation between these heights and weights. So I'm going to put along the bottom of my graph heights in centimeters. I'm going to use the grid here as my axis. Firstly, I'm going to examine the numbers. The smallest height is 150 and the largest height is 180. So looking at my grid here, I'm going to start at 150, and yes, I think it will fit. If I give each box as 2, that would be 152, 154, 156, 158. This would be 160, and there are 5 boxes between that and 170, and the same again between that and 180. Okay, so nicely spaced out. Now if I had a ruler, of course, I'd draw a nice straight axis along here, and that is heights measured in centimeters. Now up the side we have weights. We're going to put weights. Looking, yes, 57 is the smallest valued there, and the largest is 70. Okay, so not such a high range. So again, you don't have to start at 0. I'm starting down here with 57, and this is weight, so don't forget to label your graphs, and these are in kg. Okay, 57, 58, 59, 60, and hopefully we'll fit in up as far as 70. So 61, 2, 3, 4, 65, well, just about 66, 67, 68, 69 and 70, so just about fit. Okay, again, use a ruler, make it nice and presentable for an examiner. Okay, now plotting 150 centimeters goes with 57 kg, so I put an X right on the corner there. 152 goes with 62, 61, 62, so I tick off when I've done. Okay, 155 goes with 63, so 155 is between 154 and 156, and it goes with 63, which is here. Okay, that's that done. 158 goes with 64, that's there. 158 also goes with 58, which is away down here. Okay, 160 goes with 62, 163, oh sorry, that last one is wrong. Can I rub that out? Oh, I can. Okay, so the last one there, 160 goes with 62, goes here instead. Okay, and that's why we always do graphs in pencil, you can rub out. 163 is here, goes to 65, yeah, so there. 165 goes to 66, that's there. 170 goes with 65. 175 goes with 70, so that was the tallest one, or the highest one. 178 goes with 66. And finally 180 goes with 67. Okay, now that's our scatter graph drawn. Okay. Now, next we're asked to describe the strength and the type of correlation between these heights and weights. Okay, so looking at it, I can see a definite upward trend of as the height increases, so does the weight. Okay, so there's a definite upward trend. I'm going to call this person down here an outlier. Okay, they're very different from the norm, and I can enclose my data in a shape like this. Okay, it's quite spread out, but I can imagine a linear pattern there. Okay, now the thing is, if you have to use your imagination at all, Well then, when you're describing the strength, I would say weak, okay, rather than strong. And the type, it's definitely rising, so we'll say weak positive correlation. Okay. Now, something we have to consider is just because they look on a graph as if they're related doesn't mean that they are necessarily, and this is called causal. It comes from what causes the change in one other. Okay, so let's read this. The price of a used car depends, among other things, on the age of the car. The age of the car causes the price of the car to decrease. We say there is a causal relationship between the price of the car and the age of the car. Okay, so one thing causes the other. It results in the other. Definition here, when a change in one variable causes a change in another variable, we say that there is a causal relationship between them. The scatter graph shows the relationship between the sales of iced drinks, so cold drinks, and temperature. The correlation is strong and positive. You would expect this, as a rise in temperature would tend to result in an increase in the sales of iced drinks. So you can see a definite trend there in the scatter plot. It would therefore be reasonable to conclude that there is a causal relationship between the sales of iced drinks and an increase in temperature. Now, what about an example that's not causal? So the scatter diagram below shows the number of iPads and the number of fridges sold by an electrical shop over a 10-month period. Okay, so on the horizontal here we have iPads sold, and on the vertical here we have fridges. So at first look there appears to be a correlation. Okay, the graph shows that there is a reasonably strong positive correlation between the number of iPads sold and the number of fridges sold. However, this does not mean that there is a causal relationship between them. Buying an iPad does not cause you to buy a fridge, and vice versa. So correlation does not necessarily mean that there is a causal relationship, so bear that in mind. Okay, now we have a line of best fit, and I've approximated this in previous slides, where I can imagine a straight line should be. We have already stated that when points in a scatter diagram lie on or close to a straight line, a strong correlation exists. When a line is drawn through the points on a scatter diagram, it is called a line of best fit. Try to draw the line that fits best through the points. You should aim to have roughly the same number of points on either side of the line, and this method is generally referred to as drawing the line of best fit by eye. Okay, so you try and include the same number of data points above and below the line. So there's, if we look at the diagram here, there's one above, 1, 2, 3, 4, 5, and under we have 1, 2, 3, 4, 5 and 4, and you have 3, 4 on it. So that's a good approximation. Okay. The scatter diagram here shows the average daytime temperature plotted against number of ice creams sold. Okay, a line that is drawn to pass as close as possible to all the plotted points on a scatter diagram is called the line of best fit. Okay, the line of best fit, it can go through some, all, or indeed none of the points, and it is to show the general trend of the relationship between the two sets of data. And the line can be then used to estimate other values. Okay, so if I said, how many ice creams are do you think would be sold if the temperature tomorrow was 20 degrees? So here's 20 degrees, and I can go up from 20 degrees, hit my line of best fit, and then come across, and I could say, oh, about 39 or 40 ice creams. Okay, so you can use it to help you predict. However, estimated values where the line has been extended beyond the existing points is less reliable. All right. So calculating the correlation coefficient. So we don't have to calculate it precisely at ordinary level, but it's useful to see numbers, okay, put on what we talk as strong about as being strong or weak. Okay, correlations. Correlation is a measure of the strength of the relationship between two sets of data, and we use the letter R to denote what the correlation coefficient. Okay, so R is a number that describes how strong or weak correlation is. Okay, and R will always be between -1 and +1. So when R is equals 0, it means that there's no correlation, and you see that here in this diagram. There's no correlation. The points are all scattered around with no pattern. When R is equal to 1, you get the perfect positive correlation. So perfect straight line, R equals to 1. Perfect straight line but falling is the perfect negative correlation, and it has R equals -1. Okay, so +1 for a line that's rising and -1 for a line that's falling. Now here we see kind of a wide oval shape spread. Okay, and this is an example of a graph with R equals 0.5. Okay, so there's some positive correlation there, but it's not strong. Okay, we saw R equals 0, no correlation, and here's one that is quite narrowly spread out. Okay, and this has a -0.8, and 0.8 would show strong, and in this case the negative correlation. So the nearer the value of R is to 1 or -1, the closer the points on the scatter diagram are to a straight line. So here's a question on correlation. We are provided with a scatter plot, and we're asked to select the correct value of correlation coefficient. So to select the correct value of R for this picture. So let's study it. We have petal length against petal width. So we're studying some sort of flower, okay? And I'm going to enclose the data here. All right, and I can see that for sure as one is rising, as the length gets larger, then the width gets larger. That's the trend. Okay, so we definitely have a positive correlation. For that reason, I can discount the -0.2 and the -0.8. Okay, next thing I look at, how close together is all the data. So it's quite widely spread, and for that reason I'm going to discount 0.96 because that would be very, very close to the perfect straight line. Okay, so we're left with 0.5 versus 0.1. Now 0.1 basically it's very, very close to 0. It shows little or no correlation. Okay, so I'm going to discount that because we have a definite trend that we can see, and so we're left with 0.5, which is moderate. Okay, it's definitely a positive correlation, but it's in correlation, it's in the middle. It's not really strong, it's not weak. Okay, so we can, if we're undecided, we can say it is a moderate positive correlation. And you see some values here for R's and descriptions here, starting with the perfect positive correlations, perfect straight line. If your R value is 0.8 or bigger, you would have strong. As we have here, with between 0.5 and 0.8, you can say moderate. Less than 0.5, I would say weak. Okay, after that 0 is 0, and then you're going in the other direction towards the perfect negative, which is -1. You start with weak, moderate, strong, and then perfect. Okay, so calculating correlation. I'm going to do an example which leads us to calculate the value of R, the correlation coefficient. Okay, so the table below shows the weights and heights of 12 pupils. We've height in centimeters and weight in kilograms. Draw a scatter diagram to show this data. Okay, so I've done that there. We have height on the x-axis and weight on the y-axis, and we can see a scatter of data points. We can see that definitely there is a trend, which will be asked to describe. Okay, so that's part 2 of the question. Describe the strength and type of correlation between these heights and weights. Okay, so there we have it. Okay, yes, there is this one single point. Okay, out here, this is what I'd call an outlier. Okay, but if we ignore that for the time being, you can see that for sure there is a positive correlation, and that when you group them, that it's quite a narrow grouping. Okay, so I would say that we have a strong positive correlation. So there's a strong positive correlation between the heights and the weights of the 12 pupils. Now, part 3 asks you to draw a line of best fit on your scatter diagram. So there's our scatter diagram. Now, a line of best fit is a line that best approximates the trend of the graph. So if you imagine, where might a straight line describe that data? Okay, so it'll go up through the bunch of lines, and generally we'll try and count the data points so that half of them are above our best fit line and half of them are below the best fit line. So the syllabus will only requires you to do this by eye. Now, there is a section in your textbook that describes how to calculate the equation of that line, but it's not actually examinable. Okay, so to do this by eye, and I've done it already, is I would place my line there. Okay, and why? Because if I count the dots, I have 1, 2, 3, 4, 5, and 6, if I need to include that one. 6 above, and 1, 2, 3, 4, 5, 6 below. Okay, and it best for me approximates it. Now, you may choose a slightly different course for the line than I did, and so might another student. So once it's within reason, you'll get your marks for that. Okay, so now we're asked, Tony is 162 centimeters tall. Use your line of best fit to estimate his weight. Okay, so the word estimate is used. And the reason that's used is because we've drawn our best fit line by eye, and yours may be slightly different than mine, so we might get slightly different answers for this part, and that's okay. So he's 162 centimeters tall. So firstly, you have to locate that on your x-axis. Okay, so roughly about there for me. You will be using more graduated graph paper and have it done better. Okay, so let's say 162 centimeters is there, and I want to find the corresponding weight. So over there, so that's between 60 and 65, closer to 65. My estimate is going to be I'm going to say 64 kilograms. Now, you might have 64.5 or 63.5 or 63.9, depending on your graph, and that's completely allowed because it was an estimate. Okay, and finally, use your calculator to find the correlation coefficient, corrected 2 decimal places. Okay, so I've done that on the calculator here, so let's have a look at that. So in this video I'm going to show you how to calculate the correlation coefficient using the Casio calculator. There are newer versions of this calculator out, so I plan to make a video with those shortly, but they will have similar menus, perhaps in different locations, so do your best for now. So first thing we need to do is to go into statistics mode, so mode is here, and number 2, select statistics from the menu, and we're studying bivariate data on a graph, and we hope that if we get correlation it will look like a straight line. So you see number 2 here, a plus bx. Well, that's the format of a straight line. You learn it as y equals mx plus c. So we're looking for straight lines, so we're going to press number 2. Right, and here we have a blank table, an empty table where we can put in our values for x and y. So on our graph, on the x-axis, we have height in centimeters. So I'm going to enter those values here. So 150 was the first one, and press equals to enter. And you see that the calculator scrolls down. So I will continue with height values for speed. 158 is 2 of those. So entering this. So there we have it. Notice frequencies here. There's just one of each. We don't need to use that this time, so we'll leave it alone. And I can go back to a blank screen. The data is entered. I want to analyze that now statistically, so I'm going to use this function down here, stat, and I'm going to press shift for yellow writing. And here I have this menu. Okay, and to get your correlation, I'm going to select number 5 red. Okay, and we'll see where we get a lot of letters, but number 3 R is the correlation coefficient, so that's 3. I'm going to press 3 and press equals, and I get a value for R equals to 0.8 roughly. Okay, so the value for R that we calculated was, and we're asked to give it to 2 decimal places, so I'll write 0.80, and that agrees with our first description that we have a strong positive correlation. Okay, so you should practice that many times on your calculator so that you recall where to enter the data and where to get R.
Okay, so here's how to do that same calculation of the correlation coefficient with the newer Casio calculator. So, as before, we have to get into statistics mode, okay, and you'll find that over here on the menu button. And then you want to either scroll across or select number 2 to statistics and press equals to enter if you've scrolled across. So we are examining how close to a true linear relationship the two variables are. So we're looking at a line format, which on this menu is number 2, y equals a plus bx. That's the same as y equals mx plus c, the equation of a line. So we select 2 for linear. And here we see the input area, our table. We have x, we have y, there are 2 variables. And you see we have frequency in this case, and that's because I've already turned frequency on in the statistics mode when I was doing standard deviation. Okay, you'll see as we progress that frequencies are entered just as 1 automatically, and that's fine, we don't need it for this example. Alright, now I'm going to proceed and enter the data. So variable x will be the height from the table on the previous page. Okay, so let's type in all the x's first. 150, 152, 155, 158, 160, 163, 165, 170, 175, 178, 180. Okay, and there were 11 pieces of data. Now I'm going to use the cursors to go back to the top with our row 1, and I'm going to enter the second variable for weight. That's going to be y. 57, 62, 63, 64, 58, 62, 65, 66, 66.5, 70, 66, 67. Okay, now I made a mistake there, so I have to scroll back. I put one too many or one too little in one of the columns. Yes, I've done that twice now. There are two 158s, so I just have to redo the X's there. Now, okay, so that in fact there are 12 pieces of data, or 12 pairs. Okay, and you see that all the frequencies come up as 1, that's fine. So how do we get our correlation coefficient? Well, we can go back to our blank screen by pressing AC, and we go to options. This will give us the menu we need. And we are looking for, they're called regression calculations. And it's another word that refers to correlation and the linear relationship between two variables, as in does one affect the other. And that's why the correlation coefficient we didn't discuss up to now has letter R. R is for regression. So let's press number 3 to select regression. And if you look closely at your screen there, you have a number of values. The A and the B give you the values to go into your equation of the line. Alright, that may be useful if you're plotting a best fit line. It gives you the A would be the y-intercept, so where it crosses the y-axis, and B would give you the slope. And R then is our correlation coefficient, as we got with the other calculator. R is equal to 0.80.